So today I'm going to tell you about a few papers I had recently and one that's coming up on the topic of how we can look for dark matter in stars and planets. So as a brief outline of what I want to tell you about today, for the first part of the talk, I want to tell you about a new search that I came up with to look for dark matter in exoplanets, so planets outside of our solar system. So I'm going to tell you about why we care about exoplanets and why they're actually a really interesting target to consider. I'll tell you about how we calculate this dark matter in exoplanet signal, how it can be detected, and what it means for the dark matter parameter space in terms of mass and cross sections. And I'll tell you a bit about what we need next to make this search a reality. Later on in the talk, I'm going to tell you about some new limits that we can set now using stars and planets in the center of our galaxy. And then at the very end, I'm going to give you a sneak peek at a new paper I have coming out looking at Jupiter in gamma rays and what that can tell us about dark matter. So to start, what I want to convince you of in the first part of this talk is that exoplanets are new, exciting, and very powerful detectors of dark matter. So how do we get dark matter in exoplanets? So we have dark matter already in our galactic halo whizzing around, and we have these exoplanets just peppered throughout the galaxy. So dark matter can come into contact with the surface of some exoplanet. It can then scatter and lose energy and become gravitationally captured. Now, over time, this process keeps happening, and the amount of dark matter that you have in the exoplanets keeps increasing. So it's just accumulating over time. And as you start getting more of these dark matter particles settling into the core of exoplanets, they can start annihilating if it's the type of dark matter candidate that does annihilate. So it can annihilate into standard model particles, and these particles then can be absorbed by the dark matter rest mass, sort of energy, the annihilation energy coming from the dark matter can be absorbed by the planet. So as these sort of final states, the energy is absorbed, the temperature of the planet increases, and then it can radiate in infrared. So this is a detectable signal. We effectively want to just look for exoplanets that are overheated. So they're heated up by dark matter more than we would expect them to be. So before I get into more of the details about how this signal works, you might be wondering why we care about exoplanets. So people have thought about these sort of signals before in other objects. What's so different about exoplanets? So there are actually a number of advantages that we get from considering exoplanets. So the first one is really making the most of an exploding research program. So to give you some perspective, we didn't even know exoplanets really existed until about 30 years ago. And almost all of the exoplanets now that we do know exist were only found in the last 10 years. And of those exoplanets, the majority of them were really actually just found in the last 5 years. So clearly this field is really rapidly accelerating, and there are going to be a lot of new sort of surprises and discoveries. And on top of that, there are lots of new telescopes and searches that are going to be done. So many of these new telescopes are coming online. Some are already doing searches. So I've listed just a number of these arbitrarily in orange on the screen. But these telescopes are going to work together to find new data and really just learn a lot about what can we do with exoplanets. So we really have ample motivation to consider the new ways this exploding research area can be used to probe new physics. So we want to take advantage of this. The second advantage that we have is just statistics. So estimates predict that there are around 300 billion exoplanets in our galaxy. That's a lot. And of course, having 300 billion exoplanets as data points would be excellent. Of course, we're not actually going to detect all of these anytime soon, but even just a very small fraction of this 300 billion is going to give us excellent statistics to understand any potential signal as it may arise. So for some perspective to date, there are almost 5,000 confirmed exoplanets that have been found with our telescopes. And there's an additional about 5,000 exoplanet candidates that haven't yet been confirmed, but they're just doing follow-up and more studies on those. So we have a lot so far, and we're going to find many, many more in the next few years. And if you want to think about this in terms of why the statistics are helpful, you might wonder why we don't just use, for example, the solar system planets. The thing with this is if you have just one Jupiter, really it is just one data point. Planets are hard to understand, and as I'll tell you about later, there are all sorts of systematics that we're going to want to understand that are going to be very difficult because there are all sorts of things that can change what temperature the planet is and things like its formation history. But by just having all of these additional data points, we hope that on average, we will actually be able to understand what a signal is as it does appear. Furthermore, actually, these exoplanets also are scattered throughout the galaxy. So if you have lots of data points placed in different positions in the galaxy, this gives us additional handles on dark matter properties, such as its local density, for example. But more on that later. The third advantage are the very low temperatures of exoplanets. So exoplanets can be very cold because they don't undergo nuclear fusion. So at their core, compared to, for example, like our sun, there is no fusion going on, so the core temperatures are just much lower. And these lower temperatures allow for a much clearer signal over background for trying to see our dark matter heating signal. In addition, these low core temperatures prevent in part dark matter evaporating out of the system. So you can think about this: if you just have a higher temperature in the core, it can then kind of give a kick to the particles so they get more kinetic energy, and it's easier for them to escape the gravitational potential and just evacuate the star. So particularly at lighter masses, this is always a problem when you choose an object. At what point does it start evaporating? So compared to things like the sun, exoplanets give us new sensitivity to lighter dark matter. Particularly, we're going to be able to probe the sub-GeV dark matter mass regime. Fourth advantage is the size. So if you think about, for example, a neutron star, which has been a really popular sort of candidate for looking for dark matter heating signals, comparing the size of a neutron star to, for an exoplanet like a Jupiter or something called a brown dwarf, which I'll tell you about in a second, I tried to draw these to scale in this figure, but you can't even see the neutron star because they're so tiny in comparison to these giant sort of planets. So the dwarfs, the brown dwarfs and Jupiters are generally about 1,000 times bigger than a neutron star. So what this means is, first of all, they can be easier to detect than neutron stars, because if you're thinking about the flux that comes from these objects, the luminosity goes like the surface area of the object. So you have the radius squared. So it means that you can just see them better when you want to detect how bright they are, which means you can see them further away as well. So we'll be able to look much further into the center of the galaxy if we want to actually see the heating signal. They also can be easier to find by virtue of the fact they're just so big. Okay, so that's a number of the advantages to using exoplanets. Now, what sort of candidates do I actually want to use for this search? So exoplanets can be broken up into a few different categories, which I'll just really briefly go through. So the first category, which isn't ideal, are Earths and super Earths. So these are exoplanets that are kind of just like our Earth, or a bit bigger. So the super Earths are the ones that are about 10 times bigger in mass or radius, up to about that sort of size, and they're generally rocky planets. The reason why these aren't ideal for what we want to do is simply that they're not as big as other planets you could use. And because they're not as big, when they have the luminosity going like the surface area, they're not going to be as detectable. Also, because they're smaller, they're just going to capture less dark matter, so the signal is going to be less bright. So we want to just use something that's bigger. So the ideal candidate for something like this are Jupiters or super Jupiters. So these, from the name, are just like the Jupiter we have in our solar system, or a bit bigger, so about 10 times bigger in the mass. So these are ideal, they're quite big, they're heavy, they give us a good dark matter signal. So these are what we're going to want to consider in our search. Another ideal class of exoplanet, if you could call them exoplanets, are brown dwarfs. So when I say brown dwarfs in this talk, I am including, so when I say exoplanets in this talk, I'm including brown dwarfs as well. If you haven't heard of a brown dwarf before, they're kind of just like what lurks between a planet and a star. So they have no fusion going on in their core, though they can burn lithium and deuterium. But they overall have much cooler core temperatures just because there's no fusion going on. Well, there's no fusion because the core temperatures are low. So these are ideal because once they're old, they're about the size of Jupiter, but they can be an order of magnitude or more dense. So their mass is much higher than that of Jupiter, but they're about the same size. So these are excellent. So because they're more dense, they can capture more dark matter, but they're about the same size. So I'm going to want to consider these brown dwarfs as well. Lastly, there's this class called rogue planets. Now, rogue planets are planets that have been either ejected from their parent system, so they can just fly out, or they can just form in molecular clouds like stars. But these are wandering all alone, cold in dark and empty space. So they have nothing nearby, they're not orbiting something. So these are also perfect for what we want to do if they have no host star, simply because when we want to look really far into the center of the galaxy, if you have a parent star, they can be very, very bright. And if they're bright, they can just then outshine the signal in a given pixel. So if you look really far away, you kind of can't distinguish the parent star and the planet. The star just overpowers everything, and then you can't even look at the temperature of the planet. So when we go really far into the center of the galaxy, we're going to want to use either these sort of rogue planets or brown dwarfs. We don't want something that has a parent star at all. Now, rogue planets generally are more commonly Jupiter size up to about brown dwarf size. So rogue planets can have a range of masses and sizes, but they're more commonly on the heavier side. Okay, so how do we calculate now the dark matter heating signal in these exoplanets of interest? So we want to think about what are the different contributions to the temperature of the planet. So there'll be contributions from external heat. So for example, nearby stars, if they have one, or a parent star. There'll be a contribution from internal heat. So this comes from things like it's left over from formation or any burning processes that are still occurring or currently occurring, as well as some dark matter contribution. So what this looks like, the total heat is just a sum of these different contributions. And this total heat power is effectively just the luminosity. So this is the 4 pi r squared is just the surface area of the object, r is the radius of the object of interest. This is the Stefan Boltzmann constant. T to the 4 is just the temperature of the object, and epsilon kind of encapsulates whether or not you have deviations from a black body. For the talk, I'm going to assume a black body throughout the with everything that I show you. This is the most conservative case, and you can ask me about this later if you're interested. We consider other cases, but for the talk, I'll just show you black bodies. This will be epsilon equals to 1. Okay, so for the contribution from external heat, we're going to assume this is 0. So by assuming this is 0, this means we need exoplanets that are either very far from their hosts, so on like wide orbits, which will be okay for local searches close by, or we're going to want them to be not bound at all. So this is this rogue planet category, which we're going to want as we go further towards the center of the galaxy. So we're going to set this to 0. It never has a parent star that's very close by that's heating it up. For the internal heat, this is determined, so this is a cooling rate you have over time that comes from simulations. So we look at a range of simulations, so people have looked at for different brown dwarfs or for different planets at different ages, what is their sort of cooling rate over time. So we look at a range of these simulations, and we will sort of feed these into what our calculation is. And we deliberately want to choose as targets old exoplanets. So we want ones, for example, that are 1 to 10 gigayears old, simply because these planets, because there's no fusion or anything, they're just cooling off over time. And if they cool off over time, this will minimize the internal heat to give us a larger dark matter heating signal over time. Okay, now the dark matter contribution. So there's a few things we have to take into account for this. So firstly, we care about the dark matter density throughout the galaxy. So we need some dark matter density profile. As an example, we have something that looks like this. So this is the dark matter density normalized to some value, given what we measure locally. And there's some dependence on a scale radius, which is kind of just think about how much you're kind of pushing the thing in or out. And this gamma is an index, which tells you about how sharp the profile is towards the center. So you can have something that's more peaked, so the value of this gamma is larger, or a standard type of profile, which you've probably heard about, NFW, Navarro-Frank-White profile, has this value set to 1. So that's a little bit less, it's cuspy, but not as cuspy as it possibly could be. So we're going to consider a number of different dark matter density profiles, simply because we don't know what the dark matter density profile really is of our galaxy. So we'll just show you a few different cases to show you kind of the span of what we might expect. We also have to take into account relevant velocities. So one thing will be the dark matter halo velocity, because the speed the dark matter is whizzing around at kind of determines how easy it is to actually capture it in these exoplanets. And we also care about the exoplanet escape velocity. So this is related to capture as well. So it's like how easily is it going to get the dark matter in there. And that just goes like the usual sort of thing. The escape velocity squared is 2 times Newton's constant, the mass of the object divided by its radius. So we're going to put all these bits of information in together to get how much of this dark matter heat power we have. And the way that we write this is we say that, so this F, you can think about as having the cross-section information. So if F equals to 1, this means that all of the dark matter that's passing through the exoplanet is being captured. And later you can try and map this onto what sort of cross-sections this correspond to. But for now, we just have this set to 1, assuming everything that passes through is captured. And then this is multiplied with kind of like a circle area of the object. So you could think about anything that passes through the circle that is the exoplanet is getting captured. This is going to tell you how much heating there is. And then you multiply with the dark matter density profile, and then we have all these velocity terms. So we have the escape velocity, which is important. And then we also have, this is the halo velocity, particularly use the dispersion velocity, halo dispersion. So what this last term at the end is kind of taking into account is something called gravitational focusing. Being you can see that if you decrease the value of the sort of halo velocity, it becomes easier to actually capture the objects, which also makes sense. They're not going as fast. It's easier to get them in the trajectory where they come in and get captured. Okay, so how now do all of these contributions compare? Can we get a heating signal that is larger than what we expect from its, a dark matter heating signal that's larger than what we expect from just its internal heat?
Ask a quick question.
Yeah, sure.
So here you're assuming that all the heat comes from dark matter that gets captured and then annihilates within the planet, and you don't care about the annihilation cross section because it's large enough that it's basically the capture rate that's dictating the annihilation.
That's right. Yeah. So we're assuming that it's in equilibrium. So then the capture rate is related to the annihilation rate with a factor 2. And the fact
Is there a reasonable value of the annihilation cross section where that's not true?
No. So we check for the sort of size cross sections we're looking at what the minimum annihilation rate is. And you can probe both S and P wave dark matter. I mean, it depends on the object and where it is, but we have cross sections down to something like 10 to the minus 34 to 10 to the minus 37 centimeters cubed per second. So these are quite low. So this is quite easily achieved for what we're looking at.
Thanks.
Yeah, that's a great question. Okay, so the figure I'm showing on the right is comparing different contributions to the temperature of the planet. So we're just breaking them down to see can we see dark matter heating over the internal heat? Because this is the main thing that we want to compete with. So what's being shown on the x-axis, this is the distance to the center of the galaxy. So we're sitting all the way over here at about 8 kiloparsecs. If you're not used to thinking about parsec, 1 parsec is 3.26 light years. So we're sitting all the way out here. As you move towards the center of the galaxy, you can see that for these different curves, this is so that the shaded regions are the amount of dark matter heating. So on the y-axis, we have heat flow, so just amount of heat. So these different shaded regions correspond to a range of planet masses. So if you sit on, for example, this bottom line of this NFW, this is one of just the density profiles. If you sit on the bottom line, this corresponds to 1 Jupiter mass. If you're at the top line, this is 55 Jupiter masses. So this is showing that, you know, depending on what mass you choose, you get some heating that sits somewhere in this, this shaded region for this profile. We also show other density profiles. So these are just as labeled. This Birkett profile is just more of a chord profile. And the GNFW is kind of, we've taken to be the most extreme version of the NFW. So this is one that's already sharp. We make it like as sharp as you reasonably could. So this has quite a large index on it. So realistically, probably if you have a sort of a pointy type of profile, you'll sit somewhere between these two NFW and GNFW lines. Now, what do you want to compare to? You see we have these dotted lines here. These dotted lines correspond to the amount of heating just from the internal heat that we expect from simulations. So if there's no dark matter in the planet, what temperature do we expect it to have? So if it has 1 Jupiter mass, it sits somewhere down here. So then if we want to compare the amount of dark matter heating to the internal heat, you can see there are many orders of magnitude for 1 Jupiter mass. Looking at the bottom line of each of these shaded regions, quite clearly the dark matter heating is much larger than the internal heat, which is good news. As you increase the mass of the planet, it goes up to be higher. So if it's more massive, it has more internal heat. So if you have 55 Jupiter masses, you sit somewhere up here. So you would notice then, if you were comparing to the top lines of these shaded regions, it's only until you start getting in towards the center of the galaxy that you can see dark matter heating over the 55 Jupiter mass internal heat. So of course, there's going to be some optimal sort of regime depending on the mass you have and how well you can see things in different positions. So for the 55 Jupiter masses, you can't see much over in this regime, but you can see more over here. For the just Jupiter mass objects, the heating is quite large in most positions, but it's also a smaller object. So I'll talk about how detectable that is in a second. So we have these signals that look promising. It looks like they're going to outperform the internal heat, but how well can we actually realistically detect these objects? So to think about the telescope sensitivity, we suggest you use an upcoming infrared telescope called James Webb. Now, this is planned to launch October of this year. For the many of you that follow the status of the James Webb Space Telescope, you're also probably aware they've been saying this for about 10, 15 years. So hopefully this actually does launch this year and everything goes as planned. But if it does, this is really something that's on the horizon, and we're going to have a lot of data from this telescope, hopefully, very soon. Now, the James Webb Telescope is an absolute monster. So it's amazing scientifically with what it can do. This is like an artist's impression of it sitting out in space here. But to compare to the Hubble telescope, at least the primary mirror, you can kind of see for size, James Webb is massive. And it's going to be able to do a lot of very interesting science. So its sort of sensitivity is, so it's sensitive to infrared. We're looking at things like 0.5 to 28 microns in terms of what it can detect. So it has a lot of different instruments and filters. And when you want to think about how detectable a signal is, the relevant choice for what instrument or what filter you use will depend on the peak wavelength. So what I mean by that, first of all, I should also note the great thing with James Webb is it can see many planets or stars at once. So we don't have to do a dedicated search for a lot of these planets. We can piggyback on other things that are looking in, for example, the galactic center region, and try and get a lot of information all at once. Okay, so to determine how the sensitivity looks with James Webb, so we assume exoplanets radiate as a blackbody, as I mentioned earlier. And what we're going to assume is that the peak of the blackbody temperature is what sets the sensitivity limit. So how that works is, this is what a blackbody spectrum in general looks like for different temperatures. So what we want to do is we want to look at, okay, so we put through our dark matter heating sort of calculation. We use the luminosity that tells us we have some temperature that we assume goes like a blackbody. So you'll get some peak at some wavelength. And what we want to do, so this figure at the top is showing you for different wavelengths, what sort of sensitivities might we expect with James Webb. These dots that have all these different labels are different filters. So depending on if we do some calculation and we predict, for example, we have some peak that would sit here, you can tell if you look at sort of the size of the signal in terms of its sensitivity, whether or not you could see it with this particular filter. And you can, just say, I put in all my dark matter parameters, I get some particular sort of normalization on the signal, and I can see how sensitive is that relative to these filters. And I'll just look where the peak is hitting any of these sort of values. So what we want to use to do this are called the near infrared imager and slitless spectrometer if we use temperatures above 500 Kelvin. So some of them are optimized for different temperatures. And if we go down to lower temperatures, we want to use something called the mid-infrared instrument. Great. Okay, so just before I show you what our sensitivity curves look like, I'm going to tell you two brief search challenges that we have to take into account, because the question is going to be, how far into the center of the galaxy can we really see? It'd be great if we could see all the way in, because there's a lot of information in the very center, but there's also a lot of things happening in the center of the galaxy, so we can't obviously look all the way in. So the two things we want to take into account, first of all, dust backgrounds. So there's something called dust extinction. So what this really means is that you can't see through the dust. So what can happen are things like the dust can rescatter wavelengths such that you still see your signal, but it looks like it's the planet, for example, is actually colder than it really would be. So this can reduce the intensity and shift the peak of the spectrum. The other thing, and which is actually more limiting for us, is something called stellar crowding. So as you start going into the center of the galaxy, there are just more and more stars. And you reach a point where the probability of having a star in a given pixel becomes quite high. And if you have another star in the pixel where you want to look at your exoplanet, you're probably not going to be able to see the exoplanet. So they're not outshining, sort of main sequence stars, for example, generically. So if it outshines the exoplanet signal, we don't want to use it. So we're going to be limited once this stellar crowding is a problem. So what we determined was the optimal sensitivity was outside about 0.1 kiloparsec. So this is about 1 degree off the plane. So in principle, it's possible you can go in a bit further, but that's where we truncate our sensitivity, which is a little bit more on the conservative side. Okay, so how does this sensitivity look then compared to what we expect as our predictions from dark matter heating? So this is what I'm showing you on the right here. So I've just arbitrarily chosen a mass range of 35 to 55 Jupiter masses. And this is labeled like the heat power example I showed earlier. So we have on the x-axis, distance to the center of the galaxy. We're sitting all the way out here. So if you go more to the left, you're going more towards the center. The y-axis is the temperature of the exoplanets that we expect. We have this dashed line is our James Webb sensitivity. So we're claiming that you can see anything above this dashed line. So it will successfully be able to detect any exoplanet reasonably above these lines here. So what does this mean in terms of our dark matter heating signal? Well, again, for the minimum temperature, the internal temperature that we expect, so no dark matter heating. So this is like the background. For 35 Jupiter masses, you're this dashed line. If you're 55, you're up here. Any other sort of mass would be in between these. The shaded regions are the temperature we expect of the exoplanet. So in the local position for these exoplanets that are heavier, you see that the lines that we expect, so independent of the dark matter density profile, it looks like you don't really have a deviation from the internal temperature. So this means at the local position for these heavier planets, or brown dwarfs in this case, you can't see any signal. But what you see is as you go further towards the center of the galaxy, these curves start kicking up. So they're kicking up when the dark matter density is increasing and the dark matter velocity is also decreasing. So we have more of this focusing. And we see that for a range of profiles, we can actually see this signal quite clearly over what we expect for the internal heat temperature. Okay, so for this dashed line as well, this is actually showing you a signal to noise of 2 with an exposure time of about a day. So signal to noise of 2 is not the most ideal for astrophysics. It's probably like the bare minimum where you claim something's happening. Ideally, you want something a bit larger than that. So we had a look at for if you wanted, say, 10 signal to noise, which is good. That can be done in about 10 to the 6 seconds on this line. So this is quite large, but this 10 signal to noise with 10 to the 6 seconds is actually quite achievable with a galactic sort of center survey. So even looking at the proposed telescope time with James Webb at the moment, these sort of surveys are actually already on the books as something that's probably going to happen. So we can piggyback off those, look towards the center of the galaxy and hopefully extract our hot exoplanets. It's also important to keep in mind, while this line requires this larger exposure time, detecting these higher temperatures, so if the exoplanets do exist up here and they are heated, that takes much less exposure time. So James Webb can detect these temperatures much more easily than it can detect these cooler temperatures. So if you're sitting somewhere up here, you can start be looking at exposure times of under a day again, which is great. So you also see this dashed line is truncated at 0.1 kiloparsec, so we're not continuing on. That's this issue of stars per pixel and dust scattering that I mentioned earlier. In principle, you actually probably could extend this to about 30 parsecs at most. But once you start getting further into this region here, you have to start thinking about the black hole and everything else that's just going wrong in the center of the galaxy. So realistically, maybe a little bit further, but not too much further than the line that we've shown. So we can see this signal, and it looks like the dark matter heating can outperform the just internal temperature. So as a note on the different types of exoplanets that you might want to use, different masses are optimized for different positions. So for lower masses, so for example here, these are just Jupiters or super Jupiters. They're much less massive. So you see that at the local position, while you can actually have some dark matter heating that's above the internal temperature, so it means they can be used in the local position, which is good. When you start looking towards the center of the galaxy, because they're lighter, they have less of this sort of gravitational focusing, and they're just capturing less of the dark matter. So you see, you only kind of get the edge of a couple of these profiles potentially. So it seems like for these lighter masses, they're more optimal to use in the local position rather than towards the center. Compared to when you start thinking about these heavier masses, the local position is useless, but towards the center of the galaxy, you can quite clearly see a signal. So we deliberately want to use these different sort of candidates in these sort of different circumstances. So this overall gives us a new dark matter search with exoplanets. So this figure is showing you just some a mock sort of distribution of exoplanets with arbitrary 20 to 50 Jupiter masses. And what you see, so again, the x-axis is just distance towards the center of the galaxy. The y-axis is the temperature of the exoplanets. Each of these black dots is like a simulated exoplanet. So what you see happening is if you could collect a lot of this data, so you could actually measure a lot of these planets, you see you get this sort of pretty sharp uptick in the temperature of the planets. So this would be really quite a clear signal of the presence of dark matter heating these exoplanets. Compared to the hypothesis that dark matter doesn't heat the exoplanets, you get these magenta triangles. This is the same planets just with no heating. So you can see, depending on which hypothesis is correct, the predictions are very different. And so James Webb can see anything above this blue line here. So this seems like this is a great way potentially to map the galactic dark matter density, given you have sufficient telescope sensitivity and given you understand the systematics enough. So this is one of these things where it's, in principle, this can be done. In practice, this will be very difficult. But given very large statistics, depending on how many of these planets we actually can measure, it's possible this can tell us some information about sort of the gradient we expect for the dark matter density in our profile. Okay. Prospects to actually find these planets now. So we have the idea of this search, how are we actually going to make it a reality? So there are actually many candidates that already exist. They just haven't had their temperature measured, which is great. So if we're just looking in the local position, there's a table from our paper where we just point out we had a look for what are planets that are on wide enough orbits given their host star to not be heated too much, and what would their dark matter prediction look like. So there already are candidates that we could use. Ideally as well, we would want even more. And Gaia thinks they can do this. So Gaia has estimated they might be able to see up to 90,000 exoplanets in the local area, so within 100 parsec in the next few years. So that's a lot. So if we could use a number of these, that would be excellent for statistics. There are also other telescopes, such as Roman, so this before was called W-FIRST, and they expect to detect at least several thousand exoplanets in the inner galaxy. So they're the ones that could be used for our inner galaxy search. So there are a lot of prospects that in the next few years, we're going to find these candidates and we should be able to measure them. Okay, so now I'm jumping to the sort of sensitivity to the cross-section that we have. So provided we find these planets, we do measure them, what does that tell us about dark matter and how dark matter might heat exoplanets? So I'm showing you two figures here. These are in different positions in the galaxy. So the left-hand side is at the local position. The right-hand side is more towards the center of the galaxy. So I'll focus on the plot on the left. The right-hand side is the same thing, just with the lower velocity. So the cross-section sensitivity that we have. So what we're showing is on the x-axis, this is the dark matter mass. So we're assuming it's a particle that annihilates and it has a given mass, and it has some scattering cross-section, which is the y-axis. So the assumption we want to set these limits is that we have dark matter scattering in the exoplanet. It's in equilibrium and it's annihilating. So the fact that it's in this equilibrium with the scattering rate, which then gives you annihilation rate, which is the thing that you detect, allows us to comment on the scattering cross-section. So depending on the object that you can have different sorts of limits. We're showing you with these solid lines, this is roughly with the maximum amount of heating that you could have. So this solid line here is for Jupiter's. So if you assume that the bulk of the dark matter that passes through heats the exoplanet, what sort of scattering cross-section would that correspond to? So this is like the brightest signal that you could have effectively. So if you had the brightest signal possible, so this would be the most detectable signal, you would have a mass and scattering cross-section that is anywhere above this solid line. If we started thinking about if you had smaller sort of capture rates, so you have then a smaller signal, you would have even better sensitivity to the scattering cross-section. So assuming you have even better sensitivity with your telescope, you could go further down. And that would correspond to if you had 10% of the maximum capture, so just 10% of dark matter that's passing through is captured, this would be this dotted line. And then you would see anything above the dotted line. So this would be the same thing for the dwarfs. Again, the solid line shows you everything almost passing through, heats the planet. You'd have this sort of scattering cross-section. If only 10% of it did, you would have, and you could actually detect it, your sensitivity would be even lower. So what we can see comparing to other sorts of observables, so this is Earth heating on the side here. The DD is just a combination of direct detection measurements. And at the top, this is coming from cosmic rays boosting dark matter and having a boosted dark matter signal that arrives at your detector. But comparing to all these other sorts of observations, we see that we can get very strong sensitivity in this sub-GeV mass regime. So comparing to if we could really detect, say, this 10% amount of the capture rate, we're looking at about 6 orders of magnitude further down compared to anything else that exists. So this can be very, very good sensitivity, which is great. What you see on the right-hand side, so it's the same thing, we're just looking in the center of the galaxy where the velocities are lower. So because they're lower, it's easy to capture, so you have a bit better sensitivity. And again, we see we have something that is several orders of magnitude further down than anything else that we have. So hopefully this means dark matter heated exoplanets will give us some probe to either discover or exclude dark matter in this sort of parameter space. Okay. We also have sensitivity to interacting with electrons because there are electrons in these planets as well. So the previous case I was showing you was interacting with the protons. If you have scattering of electrons, the limits aren't as good compared to direct detection, simply because, I mean, if you can see here, the Jupiter's sensitivity is in the middle of direct detection, and then for the dwarfs, we only have some sensitivity if you go to this more extreme 10% of the capture rate. So you can get a little bit on the edge here. So with the electron scattering, the results aren't as strong, but it's also important to keep in mind that using these exoplanets really is a complementary probe of dark matter, in the sense that direct detection is just measuring the scattering and sort of recoils on Earth. They're different systems, so depending on the particle physics model that you choose. So in all these things I've been showing you, there was no assumption about the particle physics model, they're just really rates. But there are plenty of models where you could have a suppressed direct detection signal and the signal in exoplanets or dwarfs would not be suppressed. So in that case, for a particular model, you can have these direct detection limits sort of lifted and the exoplanet limits would hold. So it's important to think about the different ways we can attack the parameter space from that point of view. Okay, so the actions that we need to get to this parameter space and make an exclusion or actually discover something. The first thing we need is successful launch with James Webb. So hopefully that does go ahead this year and it doesn't blow up and everything goes fine. A lot of money on the line, a lot of science on the line. So hopefully that happens. And then, okay, that's the first thing we need. Second of all, we're going to really need a large statistical sample to overcome systematics. So there are a number of things that we're not going to be totally sure about when we do these measurements. If we have really large numbers, that is really going to help us understand what we expect for this signal, if it's dark matter or if it's something else. Other things that we're thinking about are sort of detailed simulations of atmosphere effects when you include dark matter. So we've since been discussing with exoplanet experts, how do we think that the atmosphere might actually be affected by having dark matter in the planets, and how would this change the spectrum, for example? It looks like this actually gives you better results. So you get an actual stronger signal when you take all these things into account. So what we did was the conservative version. You can do more and it's more detectable and it's interesting. Other things to think about are sort of simulations of these age and cooling curves with the exoplanets when you include dark matter and how much this actually changes things. Okay. So I'm going to tell you for the last bit of the talk, just very briefly about some complementary searches. Were there any questions on the first part before the bulk part, before I do this last little spiel? We can ask at the end.
I had maybe a quick little, possibly annoying question, and I might know the answer. Say you actually do detect a brown dwarf that is at 3000 Kelvin out in the field. How do you know it's a brown dwarf? How do you know it's not just an M dwarf that's fusing hydrogen and that it's at 3000 Kelvin because it's supposed to be?
So I don't think we ever expect 3000 Kelvin for what we're looking at. So here is for the sort of dwarfs that we want, for our sort of detectable region, I mean, you don't expect any other stars in this sort of temperature range, right? So we're not getting that high.
Okay, so there's no range, no part of the main sequence where you would start to actually fuse and produce something at that temperature.
Right. Yeah. So the sort of temperatures we're looking at with this dark matter heating are still quite low compared to main sequence stars.
Yeah, and I guess unless you follow that generalized NFW curve all the way up, but then you.
Yeah, but then we can't see the signal anyway.
As well.
Sorry?
Oh yeah, no, okay, that's a good point, right?
Yeah, so we can't see probably into this regime. So if you kept it going up with this would be definitely getting onto the main sequence sort of temperatures, and then potentially you'd have a problem. But I assume once you get into such high temperatures as well, this dust extinction is going to be horrendous.
Right, and you have all the stars that are between you and
exactly
all the planets between you and the galactic center that have already told you that this is going on.
Yeah, exactly. Yeah.
Thanks.
Yeah, thanks for the question. Okay, so I'm just going to tell you just really briefly for the last part of talk about some complementary searches we can do with stars and planets. And I'm going to give you some new limits now. So instead of just promising a future search where we can have some limits, what can we do right now with some stars and planets? Okay, so when we think about dark matter inside these stars, planets, you can think about two different sort of regimes. So the one that I spoke about for the talk so far was the case where you have dark matter that annihilates to these standard model particles and it's absorbed, the energy is absorbed by the star. In the case that dark matter is annihilating to some particle that's quite short-lived, this is how you get the scenario where it heats planets, simply because if it's going, for example, to gamma rays here, it's just extinguished and it's absorbed. But we can also think about the regime where dark matter annihilates to long-lived mediators, so some long-lived particle. And this mediator particle is one that just mediates the interactions, or the force. It's a force sort of carrier between the dark sector and the visible sector. If it has a sufficiently long lifetime or a sufficiently large boost, instead what can happen is it can be really boosted and then it can decay outside of the star or the planet. So the star or planet won't be heated, but instead you can look for a different signature, which is any of these decay products that are appearing outside the surface of the star. So for example, this means we could actually see additional gamma rays coming from these objects if the particle just decays outside. So what sort of objects do we want to think about for this long-lived particle sort of scenario decaying outside of the star? Just to remind you, when we think about what the optimal sort of celestial target might be, there's a few things to take into account. So one is the radius of the object. So if it's bigger, you can have a larger amount of dark matter that's captured. You can have a larger annihilation signal. It depends on a few things, but this is roughly what can happen if you have a larger radius. The core temperature is also important because the core temperature gives kinetic energy to the dark matter. And if it's very high and the particles are light, you can have more evaporation. Dark matter just leaving the system and then you just get no constraints or no signal. We also care about density of the objects. So if they're more dense, generally you'll get lower cross-section sensitivities. So thinking about the different objects we have, so for these brown dwarfs, they're quite big, they're cold, and they're quite dense. So these are good. These are a good search target. We also can think about neutron stars. So they're very small, but they're cold and they're ultra dense. These are extremely dense objects, which means you get great reach in the scattering cross-section sort of sensitivity. We can also think about things in the solar system, like the sun and Jupiter. I'll tell you about those in a second, focusing first on the things that we think are going to give us the best reach in the scattering cross-section and mass sort of combined, so brown dwarf and neutron stars. We can think about all of the brown dwarfs and neutron stars that exist in the center of our galaxy. So there's a lot of them. There's a lot of them, and we want to use all of them. So if we think about all the neutron stars, all the brown dwarfs that exist in the center of the galaxy, there's really a large population. And also in the center of the galaxy, the dark matter density is really high. So if the dark matter density is high, they're capturing a lot of dark matter. Their annihilation rate is going to be large. And then if we want to think about what is the total signal we get adding up the sort of particles we get from all of these objects, so kind of thinking about just like stacking all their spectra, you get just like an enormous blast of radiation coming from the center of the galaxy. So you're just really multiplying over all of the objects and all the particles you can get coming out of all of these at once. So this is a new type of signal that we pointed out. And this also, interestingly, if you want to think about how do annihilation signals of dark matter look from the center of the galaxy. So usually we think about just dark matter in the halo and it annihilates. So annihilating dark matter in the halo just goes like the dark matter density squared because you have the two particles that are annihilating. But this sort of signature instead scales like the dark matter density, power 1, times the stellar density, power 1. Because simply the dark matter density with 1 power is giving you what this capture rate looks like. And then if it's in equilibrium, this is giving you directly this annihilation flux that's coming out. And the amount of flux you have is going to be just multiplied by the number of stars that are giving you this signal. So this really has a complementary sort of scaling, and it's a way to get an annihilation sort of signal that can be quite large, particularly if you would have otherwise had a suppressed halo annihilation rate, such as like P-wave annihilation, for example, can be quite large with this setup. Okay, so thinking about how detectable this signature is, we want to compare with the known gamma ray data that we have. So one problem is that the center of the galaxy already has bright gamma rays, and this is actually an excess called the galactic center excess. So if this signal, you want it to be either explain the excess or you want it to be brighter than the excess if you want to set some constraints. So looking at the size of the excess, so dark matter mass here on the x-axis, the y-axis is sort of like the maximum flux that you can get out of all of these objects. And these dotted lines here are the flux, there's a gamma ray flux measured with Fermi. This is the flux measured with Hess, which is, these are both just gamma ray telescopes. Now, if we think about how bright the signal can be, if I start with brown dwarfs, which is the BD, so using all the brown dwarfs in the center of the galaxy, making an assumption about the dark matter density profile. So this gamma 1.5 is really just a very sharp profile, like more sharp than probably realistically happens. And this 1 is standard NFW profile. We see that for these sort of cases that the flux, maximum flux you can get is much larger than the signal of gamma rays that's been measured so far. So because these lines are so much higher than what we've measured so far, we can set constraints on this signal. Looking at the neutron stars, on the other hand, they do have some flux, but it's not as large as what you see with the brown dwarfs. So this is a particular dark matter density profile type, which is more extreme. Realistically, you're probably somewhere between these two. This is the standard NFW. So you see, unless for the neutron stars, you have quite a sort of sharp peaked profile, you can't see anything. So you can only use the neutron stars really with Hess, but the galactic center is a bit too bright, looking at the lower sort of masses. So we can turn these into constraints. And for the brown dwarfs, it turns out the sensitivity you have to this scenario is just massive compared to anything else that exists. So this plot is showing you the dark matter mass on the x-axis, and this is the scattering rate, so the scattering cross-section on the y-axis. Direct detection is this giant magenta shaded region. So looking on the left here, we have nothing in this sub-GeV mass regime, but using dwarfs, looking at the Fermi data, we can actually constrain a lot of the parameter space, assuming you have some long-lived particle that's decaying outside of these brown dwarfs. So we have excellent sensitivity in this sort of regime here. For the neutron stars, as I showed you earlier, you need to have more of a sort of pointy profile to see them. So that's why we're looking at these higher sort of masses over here, where the center of the galaxy isn't as bright, so you can see their signal. They'll sit somewhere in this sort of regime here. So we can get new limits now using brown dwarfs and neutron stars in the center of the galaxy. And you'll see also here, we have these shaded regions labeled sun. So you can do this sort of long-lived particle signature in the sun as well. And this has been done before. So the sun sort of limits look something like this. They're very strong. So this is something I worked on a couple of years ago. So comparing the direct detection, which is this shaded region, with the sort of sensitivity you get where you look for long-lived sort of gamma rays, so long-lived particles decaying to gamma rays, with these two different gamma ray telescopes, the sensitivity is excellent. So we see we have many orders of magnitude here. But one thing you'll notice with these limits, see there's a really sharp sort of vertical line here. This is where we have this dark matter evaporation problem. And then around 4 GeV or so, dark matter, anything lighter than that just gets too much kinetic energy and just gets kicked out of the system. So you have no limits for the sun below about 4 GeV. So you could ask the question, what about Jupiter? So Jupiter is very close by. So instead of thinking about just the very center of the galaxy, maybe we can just use something Jupiter-sized in our own backyard. And the good thing about Jupiter is it's much cooler than the sun. So it has very low core temperatures. So this is actually going to give us MeV dark matter sensitivity. So we can kind of push these curves further to the left. So how does Jupiter look in gamma rays? So we've known Jupiter exists for thousands of years, but no one ever actually looked at it in gamma rays. This is the first time this has been done. So in work I have coming up with Tim Linden, we're looking at actually using the Fermi data. So this is just public available data that anyone can download and analyze to just look at Jupiter in gamma rays. So what we found is something like on the right. It turns out there's nothing there. So what this figure is showing you is like a 45-degree region. Jupiter is like 1 pixel in the middle of this image, being it hasn't lit up, so there's nothing there. These other things you see are just other features of the galaxy as Jupiter's kind of whizzing around. This is taken with like 12 years of data. But you see there's nothing there. Jupiter isn't emitting gamma rays, at least with the sort of sensitivities that Fermi can see. So Fermi isn't seeing anything. So it has to be less than what Fermi measures. But we can use this to set new limits. So nothing's there. That's a constraint on dark matter decaying to long-lived particles that give you some gamma rays. So we get something like this. So what this is showing is compared to the last plot that I showed you, we can extend these sun limits to lower masses. And this bluish region here was this galactic center brown dwarf scenario. So we actually get a couple orders of magnitude more, and it's totally complementary in the sense that, we don't have assumptions about what the density profile is. So for these dwarfs in the center, of course, if you had just, more of a chord profile and something that wasn't cuspy, these limits would weaken a lot. Jupiter doesn't have that dependence. It's just the local dark matter density. All right. So to wrap up, so for the last part of the talk, I was telling you about signatures of long-lived particles in stars and planets. So these are complementary searches for sub-GeV dark matter in celestial bodies. So we looked for gamma rays powered by the galactic center population of brown dwarfs and neutron stars. We got new sub-GeV limits there. And I told you a bit about a new paper I have coming out soon, hopefully, with the search for gamma rays from Jupiter and the new sub-GeV limits we get there. In the bulk of the talk before this, I was telling you about the regime where we have these short-lived particles that decay inside the star, and the star or planet absorbs the heat, and you look for this overheated dark matter signal. And this is interesting because, well, for a number of reasons, but really the exoplanet program is really rapidly accelerating. So there are lots of new surprises and discoveries that are inevitable. We're going to learn so much so soon. So we looked at how exoplanets can be used to discover dark matter from this overheated dark matter signal. And we found that old cold Jupiters and brown dwarfs were the ideal sort of target. We pointed out actionable discovery or exclusion searches with these new infrared telescopes, particularly James Webb. And interestingly, potentially this signal traces the dark matter density in the galaxy. We pointed out this due sensitivity to the dark matter parameter space. This can be quite strong compared to other limits that exist. And there really are exciting opportunities to realize this search really soon. So there are a number of telescopes that could be informative, and we hopefully will have a new infrared window to the inner galaxy. So hopefully now James Webb does launch in a few months' time and we start getting all of this interesting information. So that's all. Thanks.
Thanks so much. I'll clap on behalf of everyone who's muted. That was a really, really fun talk. A lot of really clever ideas. I enjoyed it. I see, so we have time for questions. I already see a hand raised. So Chris, do you want to just go ahead and unmute yourself?
Yeah, I think I'm unmuted. Thanks very much for a great talk. I am curious, I know nothing about exoplanets. So how do you constrain, or what's the uncertainty on the natural radioactivity heating an exoplanet?
So the way that we take care of anything that's going to give you some internal heating of the planet are in simulations. So there are exoplanet experts that go off and assume different types of formation history, different types of objects of different sizes. And they feed these into simulations to tell you what do you expect for the temperature of the planet as a function of how old it is. So these are the sort of models that we use for this internal temperature. So anything that's not coming from external heat or not coming from dark matter. And you can, if you're wondering then about the sort of like the systematics on this and how much this really could vary, which is an excellent question. So we can look at the range of simulations that have been done and how much these answers vary. This is kind of the status of how we can do this at this stage. And at least for what we expect across these simulations, there is of course variation, but we never see variation as large as what this dark matter heating signal can be. So for example, for some amounts of dark matter heating, we're looking at like orders of magnitude more heat flow than what you would get from any reasonable amount of any internal heat source. So while there certainly will be uncertainties involved in any sort of internal heat source that you have in the planet, it looks like very likely this is much smaller than when you have a dark matter signal that's really, overpowering anything that would be inside the planet.
Okay, thanks. And I guess that's one of the reasons to not use a rocky planet like Earth, right? You're not going to get anything like uranium and probably not even potassium in a gas planet.
Exactly.
Okay.
Yeah, exactly. So most of the, for the brown dwarfs and Jupiters, they're mostly like hydrogen, helium. They're predominantly even hydrogen. So it's mostly just a ball of protons. So you don't have as much of those other elements that are going to be a problem for that.
I see Ning Chang has a question.
Yeah, thanks, Rebecca, for the very nice talk. So when you set the bound, most of the time you assume like the dark matter particles will annihilate and deposit all their energy into the exoplanet. Maybe this is a stupid question, but what if like a dark matter annihilate dominantly into neutrinos?
Yeah, no, that's an excellent question. And the assumption when we're setting these limits is that is not what's happening. So if you could like cook up a model where you were going all the time into neutrinos, you also wouldn't have these limits. So these limits only apply to models where you're dominantly not going into neutrinos. As a general sort of comment on that, usually it's very difficult to only annihilate into neutrinos and nothing else. So just for example, with like gauge invariance, you might expect also some other charged leptons to be there. You might expect also just in general other sort of particles to be there. But if you could cook up a version where you only had neutrinos, this wouldn't be applicable. But I think that's not generally the bulk of models that people would think about.
Yeah, thanks.
Yeah.
I don't see more hands raised, so I'm going to ask a question. Did you look at white dwarfs for that the later section of capture and then annihilation to long-lived particles?
So we didn't look at white dwarfs.
I would think they'd be more abundant than neutron stars, and they're kind of in between. They're very dense.
Right. I think in terms of the flux that you have, that like the annihilation flux that you expect, I think dwarfs were higher than white dwarfs. Sorry, brown dwarfs are higher than white dwarfs. Yeah, but no, that's an excellent point. Like that could be an additional one to consider as well. I'm not sure how their abundance actually compares with the brown dwarf. So white dwarfs are Yeah, so brown dwarfs are roughly as abundant as stars.
Yeah, your brown dwarfs would probably be much more abundant. Yeah.
Yeah, so I think the brown and also white dwarfs are not that much larger in general, I think, as well. So I think the brown dwarfs are generally a superior target to white dwarfs.
Yeah, no, I believe that. But
wouldn't neutron stars also be denser and get like a lower cross-section sensitivity than the white dwarfs, maybe?
Right. So I'm thinking I'm thinking it might be somewhere in between. So you have a higher number than the neutron stars. They're less dense.
Yeah, no, you're definitely right. Like it's an interplay of these things. Like as Joe was saying, like the neutron star definitely gives you the best cross-section sensitivity. But then when you actually think about the flux that you get, like how bright the signal looks, it's brighter from these bigger objects mostly because they have this larger area that we're thinking about, that more flux kind of passes through them. But I think you're right. I think that the white dwarfs are kind of an intermediate case, and I guess we're showing the most extreme ones. So the best reach and cross-section will be neutron stars, and the biggest flux that also gives us a pretty good reach on cross-section is brown dwarfs. But that's an excellent point, though.
There's never any danger of confusing this signal with like an X-ray burst from a neutron star.
For the population one, you mean?
Yeah.
Yeah, so I guess that the difference would be the scaling of like if you looked at the morphology of the signal, it would be very different. So this one literally scales with the dark matter density times the number density of the neutron stars. And if you had an X-ray burst, that's just not going to happen because it's very localized.
Would this signal by any chance look like a diffuse set of unresolved point sources?
You with the galactic center excess sort of direction? Yeah, so actually I didn't mention that because I was just trying to cram everything in for time, but it's actually very interesting. We didn't mean to do this, but we realized you can explain the galactic center excess with this setup actually. And what's interesting about this is, so there have been some claims in recent papers that maybe the morphology of the excess more looks like the stellar bulge than dark matter. That's definitely not conclusive yet because there are a lot of uncertainties involved in all of this. But if that's true, that had been used before to argue that the origin were these, unresolved point sources rather than dark matter. But in this scenario, actually, you get a morphology that scales with the stellar bulge that's dark matter. So you actually can do this and get that sort of morphology, a similar sort of morphology. We didn't look at this in detail though. We kind of just thought that's amusing and wrote a few paragraphs about it in the draft. So we have a note in there saying, oh, look, this actually gives you the right size. You can get the right spectrum. But we didn't do like morphology studies to really confirm how do the fits compare. It was more just a very interesting point. Yeah.